Okay. So, welcome all. Today we have Professor Biplav Basar from IIT Delhi. He will be talking on three-dimensional normal pseudo-manifolds with relatively few edges. So, welcome Biplav. You can.
Thank you, Shamir. So at first, I would like to thank the organizers for organizing this seminar series. I think this will help the young researcher a lot because they can share their research to others. In fact, in all over the India, maybe all over the world. And I'm happy to be a part of this seminar series. And of course, thank you all for attending this talk. So here I'm going to talk about three-dimensional normal pseudo-manifolds with relatively few edges. So let's look at the outline first. So I shall start with some basic definitions. Then I shall talk about the motivation behind this work. Then I shall state the main results. And finally, I shall prove the main result. So here is the definition. So a D-simplex is a D-dimensional polytope which is the convex hull of its D+1 vertices. That's mean a zero simplex is just a point or say vertex. A one simplex is just a line segment. A two simplex is just a triangle. A three simplex is just a tetrahedron and so on. Now, a finite collection of simplices in some Rn is called a simplicial complex if that collection satisfies these two properties. The first property is if you take a simplex, if you take any simplex in K, then all of its faces should be in K. The another property is if you take any two simplices in K, then their intersection is either empty or a common face of both of the simplices. Now, if you take the union of simplices in some Rn, and if you take the subspace topology, then with respect to that topology, that subspace topology, the union of simplices will be a compact polyhedron. And this topological space is called the geometric carrier of the simplicial complex K. Moreover, if that topological space is PL homeomorphic to a manifold M, then the simplicial complex K together with the PL homeomorphism is called a triangulation of the manifold M. So here we have one example. Suppose we have collection of these 6 vertices, say A, B, C, D, E, F, and these 15 edges and 10 triangles. Now, if you look at this collection of simplices, now you can easily check that that collection satisfies both properties of simplicial complex. That's mean that collection is a simplicial complex. Now, if you take the union of these simplices in some Rn, here in this figure, my n is 4. So if we take the union of simplices in R4, then if we take the subspace topology, then it will be a compact polyhedra and the topological space is RP2. That is two-dimensional real projective space, or you can say real projective plane. Then we shall say that K is a triangulation of RP2. Next, we can define join of two simplices. Suppose we have an I simplex sigma and a j simplex tau. Then the join of tau and sigma is another I plus j plus 1 simplex defined by this, that is the collection of all the convex combination of the points from sigma and tau. That's mean if you take a vertex and if you take an edge, then their join will be a 2 simplex. That is the dimension is 2, right? 0 plus 1 plus 1. That is dimension is 2. Now, by using this concept join, we can define link and star of a simplex. So let K be a simplicial complex. Then the link of an I simplex sigma is the collection of all of those simplices in K which do not intersect sigma. But if you take the simplex, if you take the join of the simplex with sigma, then the resulting simplex would be in K. And in terms of link of sigma, we can define star of sigma as well. So first of all, we take all of the simplices in link of sigma, then join with sigma. Then it will be another simplex, and we take all possible faces of those simplices. Then it will be a simplicial complex. That simplicial complex is called star of sigma. So we shall see this one in this figure. So we have a simplicial complex this, which is RP2. Suppose we want to find link of the simplex A, that is link of the vertex A. Now you can check that if we choose any red colored edges, then if you take the join with A, then we will get a yellow colored triangle, which will be in K, right? That's mean the red colored pentagon together with all of its faces is the link of the vertex A. And if we choose any red colored edge and if we join with A, then we'll get yellow colored pentagon, yellow colored triangle. That's mean that yellow colored region together with all of its faces is called the star of the vertex A. Okay. Now we have two important concepts, important combinatorial invariant. One is F vector, another one is G vector. So what is F vector? So F vector is a d plus 1 tuple f0 f1 up to fd, where fi is the number of I dimensional faces of K. That's mean f0 is the number of vertices, f1 is the number of edges, f2 is the number of triangles, and so on. So if we look at the previous example here my vertices are 6, right? We have 6 vertices. So here F vector is the 3 tuple. So 6, 15, 10. So this is called F vector. In terms of F vector, we can define G vector as well, but here in this talk, we mainly need the second term of G vector called G2. So for a simplicial complex K, G2 of K is defined by this formula, that is F1 minus D plus 1 into F0 plus D plus 2 choose 2. Observe that the F vector and G vector are not topological invariant. They are combinatorial invariant, but they are not topological invariant. Why? Because we can choose or we can have a manifold or topological manifold, or you can say topological space, which has two distinct triangulation which have different F vectors. That's mean the F vectors and G vectors are not topological invariant. But interestingly, that G2 is topological invariant in dimension 2. Why? Because for a closed connected surface G2 of S, you can calculate that it is F1 minus 3F0 plus 6. And if you calculate the Euler characteristic, then you will get this will be same as 6 minus 3 times chi of S, where chi is the Euler characteristic of S. That's mean for a sphere, we have G2 is 0. For RP2, G2 is 3. For torus and clean bottle, G2 is 6. Also from this formula, you can check that G2 is additive under the connected sum. That's mean G2 of a surface, say S1 connected sum S2 is actually G2 of S1 plus G2 of S2. In other words, for a surface, you can check G2 of S equal to 3 times, it is a multiple of 3 obviously, 3 times 2 minus chi of S, which is first Betti number. That's mean we can say for any closed connected surface K, G2 of K is 3 times B1K, where B1K is the first Betti number of K with Z2 coefficient. Next, we have another important concept called three-dimensional normal pseudomanifold. Actually, since here in this talk, I mainly focus on three-dimensional normal pseudomanifold, so I shall define the three-dimensional normal pseudomanifold directly. So there is a separate definition for pseudomanifold and normal pseudomanifold. But here I am defining only for the dimension 3. So a three-dimensional simplicial complex K is called a three-dimensional normal pseudomanifold if link of every vertex is a triangulation of a closed connected surface. That's when link of every vertex is connected and a triangulation of a closed connected surface. Now, if link of every vertex is a triangulation of a sphere, then the normal pseudo-manifold is actually a manifold. That's when manifold is a special kind of pseudo-manifold or normal pseudo-manifold. The vertex whose link is not sphere is called a singular vertex, and the vertex whose link is sphere is called a non-singular vertex. Therefore, we can say that manifold is nothing but a normal pseudo-manifold with no singular vertices. In 1987, Kalai proved that for a normal 3 pseudo-manifold K, G2 of K is greater or equal to G2 of link of its vertices for any vertex V. And we know that for a normal 3 pseudo-manifold, link of V is actually a closed connected surface, right? And G2 of surface is 3 times B1 of that surface. That's mean G2 of K is greater or equal to 0 for a normal 3 pseudo-manifold K. In fact, for a manifold K as well, right? On the other hand, 1970, Walkup already worked on this topic, but for the case of 3 manifold. He proved that if K represents a 3 manifold and G2 of K is less than or equal to 9, then K is a triangulation of a sphere. Further, he proved that if G2 is 0, that is attains this lower bound, then K is a stacked sphere. So what is a stacked sphere? So this stacked sphere is actually a boundary of D plus 1 simplex together with facet subdivision. In other words, suppose we have a collection of D plus 1 simplices. So each D plus 1 simplices is a D plus 1 ball, right? Now if we attach them randomly, then after attaching, we will get another D plus 1 ball, this, right? From this to this. And this n plus 1 ball has a boundary, and that boundary is a sphere. That sphere is called stacked D sphere. Now stacked ball has an important property that, so if you have a stacked ball, then it does not have any interior edges. That's mean all of the edges and all of the vertices of the stacked ball should be on the boundary. That means should be on the sphere only. Now, for a normal 3 pseudo-manifold K, the complete characterization of K with G2 less than or equal to 2 are known due to Kalai for G2 equal to 0, due to Nevo and Novinsky for G2 equal to 1, and due to Zheng for G2 equal to 2. But when G2 equal to 3, that was not known. And in this article recently, we give the combinatorial characterization of K for G2 equal to 3. And this problem is still open for G2 equal to 4 onwards. That's mean for G2 equal to 4 or G2 equal to 5, etc. So we prove that if K is a normal 3 pseudo-manifold with G2 equal to 3, then K, that is the geometric area of K, is either sphere or a suspension of RP2. So all of you know what is a sphere. Now I define what is a suspension of RP2. So there are 2 ways we can define the suspension of RP2. One is combinatorially, another one is topologically. So for a time being, I postpone the combinatorial definition. So let's look at the topological definition. So to define the suspension of RP2, we first take a copies of RP2 and product with closed interval 0, 1. Then the resulting object will be a 3 manifold with boundary, and both boundary component will be RP2, right? This is one boundary component and this is another boundary component. Now, if we do the cone of the boundary component, then we will get a normal 3 pseudo-manifold. This normal 3 pseudo-manifold is called the suspension of RP2. Observe that this is not manifold. Why? Because link of this vertex is RP2 and link of this vertex is also RP2. Now, if you choose any other vertex here or in this pink region or here, then you will get the link sphere. But it has 2 singular vertices, so it is not a manifold. In fact, it is a normal pseudo-manifold. So this is called suspension of RP2. Actually, that characterization, that is G2 equal to 3, was not our main result. Our main result was something stronger, and that characterization for G2 equal to 3 is a consequence of our main result. So this is our main result. So in whole of this talk, we consider the normal pseudomanifold K with at most two singularity. Now let W1 and W2 be vertices in K such that B1 of link of W2 is greater equal to B1 of link of W1 is greater equal to link B1 of link of V for any other vertices V. Now, since we have considered at most two singularities, that means if we have exactly two singularities, then that W2 and W1 will be my singular vertices. If we have exactly one singularity, then only this W2 will be my singular vertex. Okay. And in any case, V will be the non-singular vertices and this term will be 0. Now, it is known that for a three manifold with boundary, B1 of delta M is always even. You can prove that. Suppose you have a three manifold with boundary, take the double of that manifold and take the Euler characteristic, calculate the Euler characteristic. Then you can check that Euler characteristic of the boundary is even, which imply that B1 of delta M is even. And this result implies B1 of link of W2 plus B1 of link of W1 is also even. Why? So suppose you have a normal three pseudomanifold with two singularities, say W1 and W2. Now, if we delete the small neighborhood of W1 and a small neighborhood of W2, then you will get a manifold with boundary. That is manifold with two boundary components, and one boundary component will be link of W1, another boundary component will be link of W2. Thus, we have this result. Now, since their sum is even, so their difference is also even. So we call that difference is 2m. Now we prove that if G2 of K is same as G2 of link of W2, then we give the combinatorial characterization as well as the topological characterization of K. So what is the topological characterization? We prove that if this happens, if this is true, then the corresponding topological space will be this. That's mean we first take link of W1 product with closed interval 0, 1. Then the resulting object will be a three manifold with boundary, and both boundary component will be link of W1, right? Now we attach m number of handles. So what is m? M is just that difference. This is m, right? Attach m number of handles and then take the boundary cone off. So we shall see this pictorially. Suppose we have a normal three pseudo manifold with two singularities. One is RP2, another one is three copies of the connected sum of three copies of RP2. Okay. Now, connected sum of three copies of RP2 is homeomorphic to RP2 connected sum with handle, right? Therefore, we shall take RP2 product with closed interval 0, 1. Then we will get this one, and then we attach one handle here, and then take the boundary cone off. That's mean if G2 of K is same as G2 of link of W2, that's mean G2 of connected sum of three copies of RP2 or equal to 9, then the topological space will be this one. Fine. Now we can look at the combinatorial characterization. Now let K be a normal three pseudomanifold with G2 equal to G2 equal to link of W2, then combinatorially K is obtained from a one vertex suspension of link of W1 via M times vertex folding. So here we have two new terms. One is one vertex suspension of a surface, another one is vertex folding. So for a time being, I postpone that one vertex suspension. Now we will see what is a vertex folding. Okay. Suppose you have a normal three pseudomanifold K and X is a vertex of that pseudomanifold. And if you want to do the vertex folding with respect to the vertex X, then you first delete X and all of its incident faces. Okay. Then we will get a pseudomanifold with boundary, and that boundary will be the same as link of X in delta. Now, if we identify any two triangles, then it will be again a pseudomanifold with boundary, and then take the boundary cone off. Now this is called a vertex folding. Anyway, this is difficult to see, but I can show you this pictorially again. Suppose this is my normal three pseudomanifold. That means we have a solid torus with the boundary coned off. Okay. Suppose we want to do vertex folding with respect to the vertex X, and this is my X. So what shall I do? We first delete X and all of these incident faces. So we will get this one, right? Now this is a solid torus. Again, it is a pseudomanifold with boundary. Now we choose two triangles on that one. And then we will identify these two triangles. See, if we identify these two triangles, you can see combinatorially, you just pull these two triangles and then attach. That's mean you will get this pull and then attach. That's mean you are just adding one handle, right? And these two triangles are this single triangle. And then again, we can do the vertex that coned off. That's mean that boundary coned off. So this is called vertex folding from with respect to the vertex X. Fine. And the reverse process from this to this is called vertex unfolding. Now there is one observation. See how we do the vertex folding. So we first choose two triangles and then identify them, right? But after identifying, our resulting complex should be a simplicial complex. That's mean when we identify two vertices, then their distance between them should be at least 3. Now, what is the guarantee that we will get such a triangle such that the identified vertex should have distance at least 3? So suppose there is no such triangles, then we can do the facet subdivisions. Now, if we do the facet subdivisions, then the combinatorially the object will not change. That's mean it will be the combinatorially same, and G2 will be the same as well, because we are adding one vertex and 4 edges. So G2 will be also same. But after doing this finite number of facet subdivision, you will reach to a point where you will get two triangles where distance between any two vertices are at least 3. And then you can do the vertex identification. Well, so there are few more results which I want to state first. So first of one, this one. So we have already seen this proposition 1, right? So it says let delta be a normal 3 pseudomanifold. Then for any vertex V, G2 of V is greater or equal to G2 of link of V. Now this result was proved by Kalai. Now there is another result which was also proved by Kalai. He proved that let delta be a normal 3 pseudomanifold and let V be a vertex, so that G2 of delta equal to link of W2. So there is a misprint, it should be W2. And then he proved that all singular vertices should lie in star of W2. That's mean, remember that if delta has a singularity, and if G2 of delta equal to G2 of link of W2, that's mean W2 must be a singular vertex. And this theorem says all other singular vertex should be in star of W2, or you can say link of W2. Moreover, he proved that if there is a vertex which is not in star of W2, suppose this vertex is V, then link of V is a stacked sphere. So we will understand this proposition in terms of picture. Suppose you have this situation. So this is my one singular vertex whose link is double torus. this is one singular vertex whose link is single torus, and there are some vertices which are outside of link of star of W2. So suppose this is my W2. So this is my W2, and these are the vertices whose links are sphere, right? Now he proved that if link of G2 of delta is same as G2 of this vertex W2, then this will not be the situation. Then the situation will be this. That's mean the singular vertex, the other singular vertex should be in the green region, that is in the link of W2. Also, if V is not a vertex in the green region, that is in the not link of the W2, then this sphere, that is the link of these vertices, are stacked spheres. Okay, so he proved this one. Now we have another observations. So let ABCD be a missing facet in delta. So what do you mean by missing facet? That's mean the tetrahedron ABCD is not in delta, but their faces are in delta. Okay. And what is a missing triangle concept? It is the same thing. Missing triangle means the triangle will be not part of that link, but all the edges of the triangle, that is all the faces of that triangle, will be in the link. So now this observation says if ABCD is a missing facet in delta, then the triangle BCD is not a part of link of A. It is easy to see, right? Because if the triangle BCD is in link of A, that's mean BCD join with A will be ABCD, which will be in delta. But that is not the case. That's mean the triangle BCD is not part of link of A, but the edges of the triangle, that is the cycle BCD, will be in the link of A. And similarly, this is true for the other vertices as well. That's mean if you look at the triangle ABC, that triangle ABC is not a part of link of D, but the edge, that is the cycle ABC, is a part of link of D. That's mean whenever we have a missing facets, then we always have, if we look at link of the vertices, say ABCD, we always have a missing triangle, or you can say a cycle. Now this lemma says, let delta be a three-dimensional normal pseudo-manifold and let ABCD be a missing facets. Then if link of B, link of C, and link of D are separated into two parts, then a small neighborhood of the cycle BCD in the link of A is an annulus. So first of all, suppose you have a cycle or circle in a surface. Now what will be the small neighborhood of that cycle? Now there are two possibilities for the small neighborhood of a cycle in a surface, or you can say on a surface. So one option is you can have a cylinder or annulus, and another option is you can have a Mobius strip or Mobius band, right? Now this theorem says if link of B, link of C, and link of D are separated into two parts, then the small neighborhood of the cycle BCD should be annulus, not the Mobius strip. That's mean this result says this one. Suppose link of B is sphere, link of C is sphere, and link of D is sphere. Now suppose link of A is RP2. Then the small neighborhood of the cycle should be this type. That means this should be contractible. This should not be the generator of the fundamental group of RP2. Because if you take the cycle which is generator of the fundamental group of RP2, then the small neighborhood of that cycle is a Mobius strip, right? So this result says that should not be our required cycle. So our cycle should be contractible one. That's mean link of A is also separated into two parts by the missing triangle. And if we have link of A is fair, then we do not have any other option. All cycles are contractible and all cycles separated into two parts, right? Now, if link of A is torus or Klein bottle, then we have two options. Either the cycle is this type, this or this. Now, in this case, the cycle is contractible and link of A is separated into two parts by the missing triangle. And another option is the cycle can be in this way. That's mean the small neighborhood of that cycle is an annulus, but the link of A is not separated into two parts. That's mean if we say that link of B, link of C, and link of D are separated into two parts, but link of A is not separated into two parts by the missing cycle, then you can easily say that, okay, link A has a handle and the cycle will be this type. Fine. Now we have the next result. So let delta be a three-dimensional normal pseudo-manifold and ABCD be a missing facet. Now this result says let link of B, link of C, and link of D are separated into two parts by the corresponding missing triangle, and link of A is not separated by the missing triangle, or you can say cycle BCD, then we can obtain one delta dash which is obtained from delta by vertex unfolding. That's mean the vertices of delta dash will be 3 more and the edges of delta dash will be 6 more, but G2 will be reduced by 6. So what is this situation? Now suppose we have a normal 3 pseudo manifold, fine, and suppose this is my vertex A. Suppose this is my vertex A. Now it says link of A is not separated, right? And B, C, D are the vertices in the green color region here. Now it says link of B, link of C, and link of D are separated, but link of A is not separated into two parts, right? That's mean link of A should be a generator of the fundamental group of this handle, right? So what we will do, we first delete A and all the incident faces. Then we will get this one. And this is my BCD, right? BCD will be this type. Now what we can do, we can now cut along the cycle BCD. Now if we cut along the cycle BCD, we will get this one, which is commutatively equivalent to this one, right? And then take the boundary cone off this. So we can do a vertex unfolding if we have a missing tetrahedron, right? Now observe that we had this situation. So these red colored vertices we had, and then now we had 3 more vertices. What you can see here, right? We had this, now we have this. So we had 1 copies of these vertices, right? That's mean we have 3 extra vertices, and these are the extra 3 edges. Now if we are taking the cone, then we will have another 3 extra edges. So we will have 6 extra edges. Now if you calculate the G2 by the formula, you will get that G2 will be reduced by 6. Now there is another result. It says let delta be a 3-dimensional normal pseudo-manifold with 2 singularities, W1 and W2, and say G2 of delta is same as G2 of link of W2. Then this theorem says then there exists a delta dash which is obtained from delta by unstacking. That's mean delta is obtained from delta dash by stacking. In particular, we can say that delta and delta dash will be commutatively equivalent. That's mean G2 of delta is same as G2 of delta dash. But all of these vertices and edges of delta dash are in star of W2. This is very important. Now recall the result of Kalai. What Kalai proved? Kalai proved that if delta is a 3-dimensional normal pseudo-manifold And if G2 of delta is same as G2 of link of W2, then the singular vertices should lie in star of W2 in delta. But we proved that delta is combinatorially equivalent to delta dash, where not only singular vertices, in fact, all the vertices and all the edges are in star of W2 in delta dash. Fine. The proof is tricky, so I skipped the proof. But what we did actually, so we can show in terms of picture. So by the Calais result, we have this situation, right? So suppose G2 of delta 2 is same as G2 of this W2. Okay, then by Calais result, we know that the singular vertex, this one, should lie in the link of W2, that's in the green colored region. And if there is a vertex which is outside of this star, right, then the link will be stacked sphere. Now what we have proved that if we have a stacked sphere, then we can find one missing facets. That's mean missing tetrahedron in this stacked sphere. And that missing tetrahedron actually is a part of that ball, which is the boundary of that stacked sphere. So I am not going to the details of that one. So if we have a missing tetrahedron here in this sphere, then we can cut along that missing tetrahedron. That's mean we can write delta as a connected sum of delta 1 plus delta 2, where that singular vertices W1 and W2 will be in delta 1. Now if we calculate G2, we will get G2 of delta 2 will be 0. That's mean G2 is a stacked sphere. That's mean delta is combinatorially equivalent to delta 1, and the vertices of delta 1 is reduced 1. That's mean whenever we have some vertices outside of star of W2, then we can reduce the complex. Since we are working on finite complexes, that's mean after finite number of steps, we will reach to a stage where there will be no such outside vertices. That's mean the situation will be this. That's mean all the vertices will be in the star of W2. Now since G2 is fixed and G2 is actually, we can calculate G2 in terms of F0 and F1, that is number of vertices and edges. Now you can calculate that if the all vertices are in star of W2, then all the edges should be in the star of W2 as well. So this was all the results. Now we can state our main result. Now our main result says, let delta be a normal 3 pseudo manifold with the following properties. First property is delta has exactly two singular vertices, say W1 and W2. And say link of W1 is a surface SH, which is a genus H. It can be orientable or non-orientable both. That does not matter. And the link of W2 is HG, where G is the genus of that surface. Again, it can be orientable or non-orientable. And we know the B1 of their difference is even. So we assume that B1 of SG minus B1 of SH equal to 2N. And also G2 of delta is same as G2 of link of W2. Now if delta satisfies these conditions, then delta is obtained from a one vertex suspension of the surface link of W1 via n times vertex folding. So now I shall define what is one vertex suspension. Suppose you have a surface this. In this case, that is in this figure, the surface is RP2. But this is true for any surface. So suppose you have any surface and we want to define the one vertex suspension. So first of all, we need to choose one vertex. Say in this case, we choose the vertex 6, this one. Then we delete the vertex 6 and all of the incident faces. That's mean we will get this one, right? And that pentagon 1, 2, 2, 3, 3, 4, 4, 5, 5, 1, this cycle pentagon is the link of vertex 6, right? Now, to define the one vertex suspension, instead of a vertex, now we add one edge. Okay, so that pentagon, which was the link of the vertex, will be now link of the edge, link of the new edge. Okay, and for the other region, that is for the other pink color region, we just take cone from the two vertices of that triangle of the edges. That's mean link of the pink color region will be that two vertices. So that's mean we have this one. See, the red color pentagon was the link of the vertex 6 previously, right? Now it is the link of the blue colored edge, and the link of all the pink color region is the vertex 6 and 7. Now you can check that in this case, link of 6 is RP2 and link of 7 is also RP2. Now this is called one vertex suspension of RP2. Here you can choose any other surface, so you will get one vertex suspension of that surface. So we know one vertex suspension. Now we can prove our main result. Now first we assume that n is bigger than 0. Now we know that delta is combinatorially equivalent to a delta dash where all the vertices and all the edges are in star of W2, right? We know that by lemma 5. So without loss of generality, since we are working on that combinatorially equivalent object, so we can assume that our delta has this property. That's mean all the vertices and all the edges of delta should be in star of W2. Now we have a trivial observation. If UVW2 is a part of link of W1, then UVW1 W2 is a tetrahedron. That's mean UVW1 is a part of link of W2. This is a trivial observation. Now suppose UVW are non-singular vertices. That's mean they are not equal to W1 and W2. Then if this is the situation, that's mean if all the triangles UVW, which is a part of link of W1, is also a part of link of W2, then both surfaces, that is both link, will be isomorphic. But that is a contradiction because we assume that n is bigger than 0, right? That's mean this should not be the case. Therefore, we must have a triangle UVW which is a part of link of W1, but that UVW is not part of link of W2. Now, what do you mean by UVW, a triangle, is not part of link of W2? That's mean UVW-W2 tetrahedron is not in delta, right? Now we prove that UVW-W2 is a missing tetrahedron. That's mean all of the faces of that tetrahedron is in delta. So one triangle of this tetrahedron is UVW, and we have already seen that UVW is a part of link of W1. That's mean it is a part of delta. And now we use the property of this one. So we know that all the edges of delta are the edges of star of W2. That's mean the cycle UVW is in link of W2. And this will imply the triangle UVW2, VWW2 and UWW2, these three triangles are in delta. So therefore all four triangles of this tetrahedron is in delta. That's mean this is a missing tetrahedron in delta. Now since this is a missing tetrahedron in delta and link of U, link of V and link of W are spheres, that's mean they are separated into two parts, right? Now we have two options for the link of W2. Either link of W2 is separated by the missing triangle or it is not separated. So case 1, so if link of W2 is separated by the missing triangle UVW, then we can write delta as a two-part, delta 1 and delta 2. Now you can see that W2 is a part of one of them. Say W2 is a part of delta 1. Then G2 of delta will be same as G2 of delta 1, which is just a G2 of link of W2, right? Then G2 of delta 2 will be 0, that is it is a tax fair. That's mean delta is obtained from delta 1 by unstacking. That's mean delta is combinatorially equivalent to delta 1 and delta 1 is the reduced one. So we can reduce delta. Since we are working on the finite complex, so delta is finite. So after finite number of steps, we will reach to a stage where we do not have a triangles, this one, where link of W2 is separated into two parts. That's mean we will have a triangle UVW, which is a part of link of W1, but it is not a part of link of W2, and link of W2 is not separated by the missing triangle this. That's mean we can do a vertex unfolding with respect to the vertex W2. That's mean we can reduce the G2 of the complex as well as G2 of the link of W2. So after finite number of stages, again we reach to a stage where we will get a complex this one, where that link of W1 and link of W2 will have same Betti number. So they may not be same. One can be storage, another can be clean bottle, but their B2 will be same. Now delta reaches to a minimum point. That's mean G2 of delta is same as G2 of link of W2 is same as G2 of link of W1. Now that delta HS cannot take another vertex unfolding. It cannot afford another vertex unfolding. Why? Because if we do a vertex unfolding with respect to the vertex W2, then W1 will be in the reduced complex, right? That's mean G2 of delta will be the same as G2 of delta dash, which is the reduced one. But if we do the vertex unfolding, G2 should be reduced by 6, right? So it cannot afford any other vertex unfolding. That's mean this will not be the case after some stage. Therefore, after all of this reduction, we will get a 3 pseudo manifold. We call it this one, where whenever you have UVW, which is a part of W1, then UVW should be a part of link of W2. And it is true for the vice versa as well. Otherwise, we can do a vertex unfolding with respect to W1, right? That's mean whenever that's mean link of W1 and link of W2 will have same kind of triangles. And this is the definition of one vertex suspension. That's mean we had a delta with some properties, and after some vertex unfolding, we get a one vertex suspension of the surface SH. That's mean we can say that delta is obtained from a one vertex suspension of SH via n times vertex folding. So this proves our main result. Now we can talk about the corollary of this result. So let delta be a 3-dimensional normal pseudo manifold with G2 equal to 3. Now suppose delta has no singular vertices. That's mean delta is a manifold directly. Then by walk-up result, we can say that it is a sphere, right? Now suppose delta has a singularity. Then by Calais result, that singularity should be RP2. And we prove that in this case, we have exactly two singularities. That's mean that n, or you can say m, that is 0. So by our main result, delta is a suspension of RP2. So these are all about these results. These are the references. So walk-up started this kind of work for 3 and 4 manifold. Then Calais extend that one for normal pseudo manifold, and he worked, he find many interesting results. And then Nevo and Novinsky worked on G2 equal to 1, followed by Zheng for G2 less than equal to 2. And in this recent work, we worked on G2 equal to 3. That is a particular case when we give the combinatorial and topological description when it has relatively minimal G2. So these are all about my work. Thank you for your attention. So if you have any question, you can ask.
Okay, so I would request all of you to just unmute yourself and thanks the speaker by clapping. So, any questions you can ask now? So, if no questions, then let's thank the speaker again.
Yeah, that video will be in the YouTube. So you can go through, if you are interested, you can go through that. And if you have any question, you can post there, or you can ask me directly through email as well.
Okay, then I think thanks Biplab for a nice talk.
Okay, thank you.
We are leaving.
We meet next week, same time with the talk of Sajid.
Who is the next speaker, Sajid?
Yeah, next speaker is Sajid.
Okay, so
Just let me confirm.
we will meet again on the next Wednesday, the same time.
Oh, Hiranya, sorry, not Sajid.
So our next speaker is Hiranya Kishore from IT Bombay. So we will be meeting on the next same time, Wednesday at 11 a.m.